So about 30% of all raw material use, 42% or up to 42% of energy use, actually about 40% when we're talking about global primary energy use. Up to 25% of water use globally, to about 40, responsible for 40% of environmental emissions, and about 20% of solid waste to landfill. Now, when we are talking about world primary energy use, buildings take up to 30 to 40% of world primary energy use. And so if we are able to reduce energy consumption in buildings, and what we do is that we improve our performance in terms of global energy use reduction and also global environmental emission reduction, and also other areas that will be impacted by energy use reduction. Now, when we look at energy use, if we take that out, we have factors that determine energy consumption in buildings. Here I'm talking about 4 main factors. We have the building design and its construction in terms of material use, equipment selection and its operation. So we are talking about heating, ventilation, air conditioning equipment, appliances, and all that. And then the choice of fuel that you use, the choice of fuel that you use for heating, for cooking, and so on and so forth. And then occupancy, in terms of occupancy behavior. Now this applies to both domestic and commercial buildings. And so when we try to reduce energy consumption in buildings, we have to look at how we can reduce the thermal load, and look at how we can also reduce the appliance energy consumption. And if possible, if we can integrate renewable energies so that we reduce the use of conventional energy, that will be so appropriate. Now, when we are talking about thermal load, what can be done in that area? We're looking at site selection and analysis, orientation of the building and building envelope itself, shading, and passive strategies in terms of allowing, doing passive designs to allow solar and light to get into the building, and then also daylighting. So now when we're talking about energy efficient systems in terms of appliance use, that can also be looked at to reduce energy consumption in buildings. Now, in this lecture, I'm more focusing on the building, the first part, which looked at building design and its impact on energy use. So if we do that, the previous slides, if we do that, we reduce energy consumption to much acceptable levels for comfort, and also we try to maximize occupancy and reduce energy consumption. Now, the building envelope itself has to be designed in such a way that it allows a lot of light and especially daylight to get into the building, and also to minimize energy. And so we have we talk about 6 main features that has to be taken into account in the correct design of the building envelope. Now, the first one is the building shape and its orientation. When you're talking about windows, orientation and type and shading, insulation levels, air tightness, and the color. The last one will be the thermal mass. So I'll take these ones one after the other and then go through each of them. Now, The building shape and orientation, you have to consider the apparent movement of the sun. The sun starts from the east and then it will set in the west. And this has to be taken into account when you are doing the orientation, so that you minimize east and west facades, so that you have very little exposure to the sun as it starts from the east and sets in the west. And then when the sun is directly overhead, then it's not possible for the penetration to be maximum through windows at the north and south direction. And so you maximize north and south facade as well. And then you minimize the floor area that receives good daylight, and maximize the ratio of wall surface area to floor area. And also, as much as possible, locate the building so that it can receive daylight on the north and then the south side. So this is very, very important. So you normally would have an elongated building along the north-south direction, so that you would just make sure that you allow minimum amount of light to penetrate when the sun starts and when it sets. And when it's directly overhead, you can have the roof in shading a lot of energy from the sun, because then the sun is directly overhead. Now, when it comes to window area and orientation, types and shape, now the design of the window area to wall area ratio to be about 40% in the north and south facade, and east and west facade should have a minimum glazing as much as possible. And then you need to provide good insulation level for glazing and window frames, and shade all windows, maximize light transmission to enhance daylight. Windows, normally you have solar gain in the form of solar radiation that enters through the window. And then we also have non-solar heat gains and heat losses in the form of convection and radiation heat losses or heat gains. And then you have also airflow that comes in out as a result of intentional, which is the ventilation, and unintentional, which is the infiltration to and out of the building. For the purpose of glazing, for domestic application, glazing is normally to allow us to be able to view, and then it's also to allow daylight in, and also ventilation, and also it also serves as a source of heat. If you are in a cold climate, it's possible to allow a lot of the windows to allow a lot of heat to come in when it's glazing. Now, for commercial applications, it's also similar, but in terms of ventilation, maybe not so much, because then you have mechanical ventilation systems provided, and also heat sources provided. This is where it's very, very important for us in Ghana to take these things into consideration in the design of our windows, especially with the new glazing systems that are being used around. Now, glass allow what we call shortwave radiation to enter, and then when the radiation enters, hit any part of the room or of the house, much of it is converted into long wave radiation. So it's possible to allow the short-wave radiation to come through, and does not allow much of the long wave radiation to escape, and therefore it builds up heat in the house, or if you are in an office, it builds up the heat in the office. And this is very important when you are in a cold climate and you want to make sure that you want to reduce the mechanical heating that you want. And so you design the house in such a way that you have enough solar energy or sun's energy coming in, enough light also coming in. And then when the short wave radiation is converted into long wave radiation, which is in the form of heat, it's very difficult for it to escape. And so you have the heating in the room. Glazing types, we have different products that are available. Double glazing, and double glazing, you can have the as an insulation area, or filled with other gases, or filled with transparent insulating material. Or you can also, because if you have air inside, air can absorb the heat, and then it's possible that as the movement moves and hit the walls of the glaze of the glass, the heat will be transmitted through the outside or through the inside. So if you want to also, it's possible to evacuate the air so that you have vacuum, so that you reduce the heat losses in that respect. Now, so you reduce convection heat losses in that respect. So it's also possible to have heat absorbing glass or reflective glass or low emittance coating, so that it allows, as I said, the short wave radiation to enter, and then also reduce the emittance in terms of when it is in the long wave radiation. So this is very, very important for us, and for us in because when the short wave radiation enters the building, it will be converted into long wave radiation. Normally, it's very difficult for long wave radiation to escape. And so this aesthetics that we want, we should also be aware that it comes also with some energy demand. And this heat that builds up has to be taken away with air conditioning system. And so if you are in cold climate, you are looking at low emissivity windows in a wavelength range of transparent in the wavelength range of 0.3 to 3 micrometer, and then low emittance in the range of 3 micrometer to about 100. And if you are in a very hot climate, you want to also have the transparency in the window of 0.3 to 0.7, and then 0.7 to about 100. Now, windows with dynamic optical properties, switchable windows or smart windows are also possible to be used. And so you have electrochromatic material that transmittance changes due to an applied voltage. So you have a voltage of up to 5 volts and sided, and it's therefore possible for the transmittance in terms of light flows to change. Now, photochromatic material transmittance will change due to change in light levels, and then the other one, the last one, chromatic material transmittance changes due to the change in temperature. Now, so the glazing properties has to be in such a way that solar gain coefficient in terms of a fraction of incident solar radiation that is admitted through the window, and then the low value terms of less solar heat transmitted. So you want to have as much solar energy in the short wavelength getting in there, and then as much as possible reduce the energy that goes out. Now, if you look at the grazing properties in terms of R values, in terms of resistance to heat, loss, these are good if you are using the U factor or R factor, which is the inverse of the U. Now, visual transmittance measure of amount of visible light that is transmitted. A high visual transmitter is desirable to maximum daylight, to maximize daylight. So you have double glazing with high solar gain, in other words, low E glass that allows 70% of solar heat to be transmitted through the glass, and also about 75% of visible light to be transmitted through that. And then you are talking about U values of about 0.3%. And then if you look at U value of about 0.24, that will allow about 27% of solar heat to be transmitted through, and then about 64% of visible light to be transmitted through. Now, shading is also another aspect that you have to provide. You have these windows. It's possible that you don't want a lot of heat to be transmitted into the room at a point of the day, or shading that will for the north, adjustable vertical shading for example, or use external shading in preference to internal shading if it's possible to use external shading in terms of trees and things to have. That is thermal mass. Now, when we're talking about thermal mass, looking at the possibility so that it could be used during the night if you need heating, or if it's for cooling purpose. You can also absorb a lot of the heat during the daytime when it's very hot, and during the nighttime when it's cold outside, it's possible to have a ventilation so that the heat would be emitted outside. Now, thermal mass is also another important factor that has to be considered in the design and construction of building, and it can be used for both cooling and heating purposes. You need to be in good, this thermal mass need to be in good contact with the air for effective heat transfer. So the thermal mass could be, the best area would be on the floor and then the walls, so that especially the floor area is where you try to introduce a lot of thermal mass so that you can absorb a lot of energy during the daytime, so you reduce the need for cooling, and then during the night it's possible for the heat to be lost. Now, insulation is also another area essentially to reduce unwanted heat losses or gain in the space where comfort is being sought. An option for ceiling, walls, and floor insulation depending on the application. Ventilation can also be used for cooling and need to be controlled as much as possible. In air-conditioned buildings, unwanted infiltration or loss of air will significantly increase the load on the heating, ventilation, and AC systems in terms of windows left open when air conditioning is operating. In domestic situation, you need to be able to control when ventilation should occur. And then the last, but not the least, is landscaping, which can be used to assist in creating comfortable conditions in any building. We have wind breaks, shading, and evaporative cooling for nearby areas of water. Now, overall building performance, if you take all this into consideration, together with appliance energy use in terms of air conditioning, energy use for your appliances, and all that, the overall performance for domestic buildings, you need, if you want to assess the performance, you need a very good house energy rating scheme, which is a tool to differentiate between very good buildings in terms of energy performance and not so bad ones. Requirement normally to select a very good house energy rating scheme should be about 4 factors should be considered. The requirements should be very, very specific in terms of reasonable detail, allowed to investigate the effect of building details and so on. Should be fast to reduce cost and allow options to be explored. Should be very accurate to give useful result, and it should be understandable. The result should tell complete story. Now, if you talking about some examples in terms of housing energy rating scheme programs, we have nationwide housing energy rating scheme program. This is very used in Australia to assess performance of buildings. First rate, but these are some examples of how you can use existing performance rating systems, examples of rating system that you can use to differentiate between buildings. Accredited users of these are normally Association of Building Sustainable Assessors, and they use to demonstrate compliance to building codes, Australia requirement, and debate continues on their validity and accuracy. Now, many approaches to building energy efficiency standard for commercial buildings. In fact, if you want to determine the building energy efficiency standard, you can specify this performance in terms of component level, that the insulation should be X square meter Kelvin per watt in terms of maybe R values. Compliance at system levels can also be used in terms of criteria for envelope systems. Overall loss coefficient, the building should be about Y, or compliance at the whole building levels, where you say that the building should consume at least not more than set amount of energy per square meter when we are talking about specific energy use parameter of the building or building energy index. And these are examples that can be used to differentiate between buildings. Now, buildings of the same type, which are perform the same functions, should consume amount of energy that should be comparable in terms of specific energy use parameter. And this system level compliance can be used to differentiate between energy performance of buildings. Now, in Australia since 2006, the building code has contained energy efficiency measures for all building classifications. The inclusion of energy efficient measures in building code Australia is part of comprehensive energy building, energy being undertaken by Australian state and territory government to reduce greenhouse gas emissions. And when we look at the building code, started somewhere in 2003 with provisions for housing, and then in 2005 they have multi-residential building provisions introduced. 2006 non-residential building. The housing stringency in terms of residential housing was strengthened or was increased. In 2010, we have non-residential building performance standard increase, and multi-residential building performance also increased, and housing performance also increased. Now, for domestic housing, energy efficiency provision added to the Building Code of Australia should normally provide for floor, wall, and roof insulation, control of glaze areas, and the provision of appropriate shading, enhanced ventilation in warmer climatic zones, ceiling conditions, spaces in cooler climatic zones, and insulation, insulating buildings, services, supply duct and piping. So for each of the territories in Australia, you have in the building code material that can, in areas will require the use of certain material with specific R values. Certain areas will require the use of materials with different R values and so on. And they have different requirements for different climatic zones. So we have 8 zones in Australia, and it's deemed to satisfy provision. If you do not go by this zone in terms of requirement, what to be used in terms of R values and so on, then you may want to demonstrate that the material that you are using will actually be able to provide the needed requirement in terms of energy use and energy consumption. So we have what we call deemed to satisfy provision. If you do this, you are okay. For example, in climate zone X, use R2 ceiling insulation. Then if you do that, then you are fine. You have to follow that. And you need to demonstrate that your design achieves the same level of thermal performance as that achieved by the deemed to satisfy provision. So even though they have this requirement, you can do something otherwise, but you have to make sure that that will actually meet the performance that the building is supposed to achieve. Now, initially, provisions were kept relatively simple for ease adoption in terms of energy efficiency equivalent to 3.5 to 4-star rating were started with. So they have different territories, eight different blocks where the building code apply in terms of the specification, what material to be used, what R values to be used, and so on and so forth. Now, in recent initiatives, we have domestic housing. After the introduction of provisions, some states and territories indicated a desire to increase otherwise energy performance of the buildings. So ABC decided to move to a 5-star rating of energy efficiency and later to a 6-star level. Now, effect of these changes are investigated through studies of expected cost and benefit. Example, the range in outcomes for homes is between a net saving of up to $8,000 and a net cost of up to $2,240. Now, recently we have domestic housing information sources that could be accessed. So consumer guide and technical manual providing information on how buildings can be constructed, the material to be used and so on. Now, residential buildings other than housing, example apartments, energy provision for class 2, 3, and 4 buildings were included in the Building Code 2005 for adoption in May 2005. The measures include provision for the building fabric, glazing, natural ventilation, building sealing, and engineering services, so on and so on. Now, for commercial buildings, offices, shops, warehouse, factories, healthcare buildings, auditoriums, and schools, energy provision for class 5, 6, 7, 8, 9 buildings were classified in the building code. Now, these classes are different in terms of their performance. So the higher the class, the better the performance. The current provision for class 2 to 4 buildings were extended to these building classes. Now, deemed to satisfy provision were extended and included significant changes to building fabric, external glazing, heating, ventilation, and air conditioning, lighting, and power requirement. Now, stronger energy efficient provision proposed for 2010-11 relating to the design and construction of new commercial buildings and also major renovations were also taken care of. This involves more efficient construction, walls, floor, glazing, and ceiling, heating, ventilation, and air conditioning systems, lighting types and power controls, hot water systems, swimming pools, and spas. And preliminary research indicate that these measures will produce savings that will be greater than the cost of updating the buildings. So we have Green Star, which is also a comprehensive national voluntary environmental rating scheme that evaluates the environmental design and construction of buildings. 9 categories included within all Green Star rating tools are management, indoor environmental quality, energy, water, transport, material, land use, emissions, and so on. Now, then other rating in terms of other rating provisions or numbers, we have building on the basis of measured operational impact on the environment. The key impact factors are energy use, water use, waste, and indoor environment. Now, these provisions are very, very important, and it has helped in terms of energy use in buildings. Now, in Ghana, we also have a building code that previously, we used to build regulations in terms of the material use, in terms of the energy requirement, and so on and so forth. Now, since I think 2018 or so, we've had the building code for Ghana, and this building code contains regulations which can be immediately adopted or enacted for use by various departments, metropolitan assemblies, municipal and district assemblies, private and public bodies. And it lays out a set of minimum regulations designed to protect the safety of the public with regards to structural efficiencies, fire hazards, and health aspect of buildings. Now, the building code normally set out the minimum performance. And so what you achieve the building code is what is required, but you can achieve more if you have the capacity in terms of the cost impact and so on, to be able to provide material that can help you to improve on the performance of the building. Now, in Ghana building code, I went through, and the part 13 and 14 normally talks about energy efficiency. And those two sections relate directly to building energy efficient buildings in Ghana. Now, part 13 normally look at the interior environment. It provides minimum provision for interior of the building in terms of occupied environment, ventilation, lighting, and space heating are directly regulated in this part. Minimum room size and maximum room-to-room sound transmission are set out for certain occupancies. Now, the code governs ventilation, temperature control, lighting, yas and quartz, sound transmission, room dimension, surrounding materials, and prudent proofing associated with interior space of the building. Now, in terms of energy efficiency and sustainability, you have the part 14, which sets out the requirements and recommendation for energy efficiency in respect of mechanical ventilation systems, refrigeration equipment, hot water systems, and lighting systems. And these shall be designed in such a way that it meets minimum performance standard. Or if you are acquiring them, you have to make sure that they meet certain minimum performance standards. Now, performance requirements in terms of service and equipment in buildings shall be as energy efficient as practicable and facilitate the conservation of energy. And refrigeration and air conditioning appliances shall meet as prescribed by law. So we have, in Ghana, we have minimum energy performance for refrigeration and also for air conditioning. And these minimum performance standards have to be met if you introduce these appliances in the building. Now, general strategies for energy efficient building, as go over again, you have to minimize losses and maximize solar gain, heat gain cases, and then maximization of electricity demand for artificial lighting. And therefore, when we are in terms of compactness, we have transmission heat losses play an important role, as we have seen, for the energy performance of building. Depending on building type, whether it's housing, office, school, and others, transmission losses can have the highest ratio of all energy losses. Therefore, the first design relevant measure should be reduction of heating losses by minimization of this shape volume ratio, especially for an economic realization of passive houses. Zero and plus energy houses compactness is of highest importance, as worse compactness means higher construction cost. So in terms of solar gain for heating cases, in the heating period, if this may not necessarily apply to Ghana, in heating period, maximization of passive solar gain should be the main target to reduce heating energy demand, and optimize interaction of orientation, size of window, and disposable thermal mass are the key elements. Minimization of solar gain for cooling also must be adhered to if you want to make sure that you provide enough cooling load. This is very important, and this applies to us here in Ghana. Orientation and size of transparent building element have important influence on the cooling demand. And this may be in Central European climate. Pure south orientation is the best orientation for reduction of heating and then cooling energy demand. Ninth, ventilation. In office building, up to about 2/3 of the total cooling load can be managed by passive cooling. So it's good to build a house in such a way that you allow enough ventilation to allow for this to be possible. Night temperatures around 15 degrees, adequate thermal building mass, and the possibility of natural stacked ventilation are requirements for this kind of cooling. So natural ventilation by wind for high-rise building, natural ventilation constructed by wind are innovative alternative to conventional mechanical ventilation system. For new office building, a lot of these things that I've talked about were provided in the regional orientation south facade maximized as much as possible. So that can be seen there. And then in terms of energy efficiency design for our CIS building, the maximization of daylight was efficient. Low windows and glasses were also introduced. And we have also introduced a possibility for natural ventilation. We will not need so much artificial lighting. And then the heat that is built up is transported through the air flow out direction. So this is a concept that we design, the architect design with input from the center, and this building is almost near to completion, and it will be commissioned hopefully in February. Now this was possible because we have experts from different areas who may discuss the options that could be used to improve the performance, the final how the building will look like when it's completed in about 2 or 3 months' time. Now, so minimization of electricity demand for artificial lighting. Now, besides heating and cooling, the energy demand for artificial lighting is of importance for energetic performance of buildings. Buildings with huge overall widths, like office buildings, tend to have substantial energy demand for artificial lighting. Therefore, development of innovative daylight concept the most important strategy to decrease energy demand for light. Daylight concept always have to be considered in the combination with aspects with other aspects. Of buildings, and on the other hand, the use also has strong influence on the environmental performance of the building. Hello, Mubarak.
Hello, Prof.
Hello.
Hello, Prof.
Yes. So Gustav, yes, okay. So Gustav has his hand up. Gustav.
Okay, all right. Yeah. So, Prof, can I ask my questions?
Yes, please.
All right. Yeah, that's a nice presentation. Even though I didn't follow all through, I joined somewhere the line. But as you present, on there's something that I've observed in the North, and I don't know whether your presentation has addressed that or you can address it from your experience. Looking at our building very, very warm, and at certain times of the year, is virtually unbearable even staying indoors. But you are talking about building codes. First of all, let me ask, do we have different building codes for buildings down south, maybe in the forest dice? What about Ghana? During the peak of the heat period, we virtually have to depend on, for instance, air conditioning so that we'll be able to stay indoors. And in a way, in CSM, as the Ministry of Health always helping us to advising us to use ventilated rooms. Don't you think that during the heat period, if electricity rates can be reduced for those who are in the north, upper east, upper west, Savannah, northeast, and maybe some part of the Brown regions? How do you think about that? So that we'll be able to use air conditioners, because it has become a necessity. It's no more a luxury. Yeah. So these are my questions and probably inputs.
Okay. Yes. Thank you very much, Gustav. In fact, the building code is supposed to take care of the location and then the kind of material that could be used for a given location. Now, as I showed the one in Australia, which is very comprehensive, that I'm very familiar with, it specifies the different materials that could be used for different parts of the country. And in Ghana, shouldn't be that different from that. If we want to do proper building code, it should take care of the location, the type of material that could be used, and so on and so forth. In fact, I started going through the building code for Ghana today. I haven't really have a very detailed look at it. But in terms of material that could be used for different parts of the country, I suspect this should have been taken care of. If it's not been taken care of, I mean, those people here who in this forum who have experience with that can tell us. But so that is something that I do not endorse that much for this country. In fact, the louver bridge that we used to have, which has allowed airflow as much as possible, have been the best. Now, in the north, if you want to use glazing, it should be such that either has some of that is something that can be debated because, you know, if you only look at the comfort level that you want to provide for the occupancy have to be reduced because it's at that period that a lot of energy is also used. And utilities will need to recover their costs anyway. And therefore, if they have to provide more energy or during the peak period that, time, their cost has to be covered. And if you suggest that subsidies have to be given for the people in the north during this period, then somebody else has to pay for this cost. Whether the government will be ready to do that is a difference about the comfort level, but how could the comfort level be provided? It has to be provided by electrical energy, and somebody has to pay for it. Now, if you have cost accumulation, if you talk to most of the utilities, they have issues with recovering their cost. So this is another issue that can be looked at. So thank you very much. I don't know if I've answered your question, but
thank you. You have. Yeah, you have. I'm grateful.
Yes, Prof. Thank you very much. My network has been stable now. Yes, there's another question in the chat, and it's Shea Baba. He wants to find out what is the effect of a high roof of a building on its cooling ability. Because it's something that we've all observed that now the roofing styles are so huge, so high. Yes. So he wants to find out what is its implication on the cooling of the building. Thank you.
Yes. So that provides enough volume in terms of the dimensions to volume ratio, and so that if you provide enough volume in terms of you provide tall roof, you are increasing the volume of the space, and that is very good when it comes to energy use, because then you have not so much conduction and so on to the walls and the roof area. So the roof area is where you lose a lot of energy. The roof area is where you can lose a lot of energy. And if you
Hello, Prof. Hello.
So let me, yes.
Yes, there's another hand up. That's Rakesia Gmail. Please unmute your mic and ask your question.
Well, thank you so much. This is Raymond Kase. So much, Prof. Good presentation. I think you've touched on very important elements relating building codes, building structures, and energy in general. But I thought your presentation was going to look directly at two areas, residential accommodation and office space, more or less. So you're looking at commercial and private settings. I think you've done quite a lot in explaining what the commercial parts will look like in terms of looking at the efficiency. But I'm still struggling to catch what the input will be for more domestic. And the very first question was highlighted a few things regarding the domestic, and I would want to dwell a little bit on that area. So I'll give you just what we know on the ground. So for example, in Tamale, if you went to communities like Uko, you went to communities like Sodo, you go to communities like Watke or Gumani. These are communities that UDS serves. You would imagine that there are windows there, all right. The houses, the domestic houses have their windows. But what you would find interesting is that they would still put plastic on the windows and seal them off. They seal them off mainly because of dust, because they find that during the day, even if the window were shut, dust had influence in the comfort that they had. So as a result, thermal comfort was compromised for sanity, if you want to say, if that's were going to be impairing on their sanity. So that becomes an issue that you want to say that how do we break through in dealing with thermal comfort in domestic homes, vis-a-vis the fact that there is the need to increase ventilation, yet the people who occupy these places do not see that the vents are serving their purpose, more or less serving their purpose and not giving way for others. Now, there have been other schools of thought that has said that let's try and open a few more vents below to carry cool air in, to excrete more hot air. That has also opened the door for others to think of invasion of reptiles and other animals that may not be welcome in our homes. So there has been a very huge discussion in this area looking at this subject. And therefore, if we need to look at thermal comfort and looking at the balance between energy and our buildings, that we should look at what is needed in the certain areas. And that's what I take from your presentation today. Maybe as a matter of first steps for the Energy Center is to learn from the things you presented on the zoning in Australia. If we're able to do some good zoning in Ghana, where we are able to clearly identify areas for which we put them in certain climate zones, and therefore certain minimum might gives us a set of tools or set of ideas as to how this could be modified. And the building codes, the very latest ones were released just a few months ago. And some of them even sizes. But I'll tell you, and some of you probably do not know, the building codes have even have abrogated the use of using touch in certain areas of Ghana. So you can't even roof your house with touch anymore at certain parts of Ghana. And these things, we've identified that touch roofs give us the best of comfort in terms of thermal comfort. But obviously, there are other impacts that have come to hit the touch roof usage. So obviously, scarce, and the fact that you have to change them very often and they were not very durable became another issue to discuss. But all in all, I think zoning will help us really start to adopt to a set of conditions for each zone, and set that certain minimum conditions must be met in a way that some of these things can be well addressed. I think the School of Engineering is also helping to investigate a little.
Taking into account if it's not done yet in the Ghana Building Code. So thank you very much, and this I like your input. Thank you very much.
Yes, thank you very much, Prof. Raymond Kesse. He's the head of the Department of Waterways and Environmental Engineering in the School of Engineering, University for Development Studies.
Excellent, excellent. Thank you very much.
Yes, there is one last hand, then we can wrap up.
Yes. Yes.
Baba, please, Baba, you can unmute your mic and ask your question. I think this will be our last question, then we can end the webinar. Hello, Mr. Baba. Hello, Mr. Baba.
Hello, can you hear me?
Yes, please, you can ask your question.
Okay, thank you very much. Prof, please, in the olden days, you realize that in our villages, you said you are not familiar, in the northern part of the country, but in the olden days, especially in this part of the country where we live, you realize that they were building round houses with thatch on top. When you enter inside, you realize that it's more than air conditioning. Yes. But now, we are moving away from that. We now have zinc on top of our roof. When you enter inside, it's more than an oven. So now looking at these two, which is the best? Is it the modernity or the olden system? So,
yes, these are the issues that we are dealing with in our time, and I think we have to go back to the drawing board and see where we have gone astray. And now that we have the Energy Center and then the School of Engineering, I think they should lead the way and let us know what the impact of these new designs have been. So once we have the data, as you have said, that these days it's very hot inside, previously where we have the surface area not so much exposed, and it's more in cylindrical shape, you were having a much colder or comfort in the buildings. So these are areas that our research should focus and should give the direction in terms of where we can advise the authorities in terms of regulations and what should go into the building code and all that. So I'm grateful. I think this has opened a window for us. For us here from Sunyani, I think we can partner with UDS and with the Energy Center in some of these areas so that we can work together to find a solution to some of the problems that are being faced in the north. So thank you very much.
Thank you, Prof, for the response. Our dean, the dean of the School of Engineering, has joined us. I want to see if he's still there and if he wants to. Oh, unfortunately, I think he's off again. So thank you very much for the presentation. We are very grateful, and then we extend our gratitude to all those who participated. And we hope that future webinars you will make time to join and then we'll all together learn new things, especially to become energy conscious. Thank you very much.
Thank you.
Yes.
Thank you very much.
Somebody is asking about the slides. I'll talk to Prof. Those who registered for the webinar, we'll see how we can share the slides with you. Yes. And then from Mr. Kenneth Tam, one of our collaborators in Canada, University of Alberta, is also saying that the presentation was great. And thank you very much for your time. Okay. Then,
thank you very much.
Bye.